Today was a fun day. I decided to catch up and learn a little bit more about approximation theory. So I was reading about that. But from other side, I thought that I never visualized and never programmed it. It doesn't take a lot of time, just literally like not like a couple of minutes, but 5-10 minutes to visualize a p-norm. Because we know whenever we have the metric space, we have the notion of the distance, but the notion of the distance can be induced by norm, which can be also induced, but the norm itself can be induced from the inner product on the vector space. So that's why what was interesting, there's a specific type of norms called p-norm for Rn. And I wrote a short code which is visualizing how the unit ball changes for the value of p-norm between 0 and 20. And I'm going to show you this right now. So you can see here, if I'm going to run my animation for the code that I wrote, we're going to get the following ball. So in this case, when p is going to be equal to 1, we exactly is going to get the norm which is given as a sum of the absolute values. In this case, absolute value of x plus absolute value of y. If we will continue running this code until p is going to reach 2, not 2.1, but 2, that's exactly is going to be a regular unit ball that we know. And for the higher values of p, when we're going to keep increasing them, you can see when p goes to infinity, we exactly is going to have infinity norm, which is given as a maximum of the absolute value of x and absolute value of y. Also, I read this interesting and amazing paper. I learned a lot from it about splines, rational functions, and neural networks. And half of the paper were pretty clear to me up to a certain page, and you can see the page when it's not clear anymore when I don't do any annotations. And I actually learned a lot and found a couple of good sources to continue reading. And what I'm surprised, that people starting from 1960s, 1970s, they have such beautiful and amazing work with so many insights. And some of those papers have only 5 or 10 citations, and that's really upsetting. I don't remember how many citations this paper have, but I enjoy it a lot. It's a really good paper, and I'm going to probably, if I'll have time, to do some review of it, of the topics and the things that this paper discussed. Another paper that I have read is Supervised Learning for Probability Distribution by Neural Networks. The beauty of this paper that I think a high school and early undergraduate student can read it, because they introduce so gently and lightly all of the modern objects of study, like neural networks, like functional space, probability distributions, like different metrics, loss functions and stuff. And the language in which it's written it's really, really good. I enjoy this paper. There is a couple of insights which I got from it. Overall, the idea, what I was looking for, I just want to there's a huge theme about that. Whenever you construct different architecture for the neural network, you will set up that this neural network is going to live in a certain ambient space. It's called also latent space, as I understand, among computer science community. I like to call it the ambient space, because when you have the architecture of the neural network, it's going to be a function, and function belongs to some class of functions. In math, we can give a concrete description for that space. First, we can define the space as a set, then we will need to impose some topology, and there are different topologies, and the fun begins basically. But in this case, I just wanted to know to look at the work or overall the history, how people think about neural networks as they're learning certain type of probability distributions, and how picking different architecture of that probability distribution of the different architecture of the neural network will affect what kind of different probability distributions we're going to learn. And I feel like I will just do one long video. By long I mean like more than 10 minutes probably. As I like to ramble about math, so for those like 2 papers, and I will go over them and just share my insights, and at the same time it's going to be a good review for me to see, because the best way to make sure that you understand something is to try to explain this thing to someone else. That's the best part of teaching. Yeah. Anyway, thank you for watching, and let me know if you have any questions about either of those papers, or if you know personally some good papers, and can you recommend them to me so I can take a look at them. Because one more thing is, like, recently I read for the first time Double Descent, the original paper from 2019 I think, or 2018, I don't remember. I also I would like to do some experiments regarding that paper, and also can do review of it, and that paper is really good. I was quite surprised, and I like it a lot. And for me it's interesting whenever you read some other people experiments and stuff, and then you can go and do it yourself. That's the best part of involved in research. That's the best part of being a researcher, and just exploring and having fun of trying to connect the dots. Like, we ourselves, like as people, as a sort of neural network and machine learning algorithm, as we observing the world through our senses and trying to make sense out of it.